Okay, for this lesson, we're going to take a look at the multiplication of rational expressions. Now, the nice thing is multiplication of rational expressions, much like when we multiply fractions, is actually a simpler process than adding or subtracting. You don't need to find the lowest common denominator or anything like that. All you're going to do is you're going to multiply straight across the numerator, straight across the denominator, and then you're going to simplify. So if I take a look at example 1 here, then I could say that this is all the same as just putting it straight over top of here. I'm going to multiply the top, and I'm going to multiply the bottom. So 7 times 1 is just 7, and 10 times 5 is just 50. And I'm done. Because I can look at it that way, when I get to example B, then I don't need to look just at simplifying directly over top of the fraction. I can simplify any number that's being multiplied in the numerator from any number that's being multiplied in the denominator. Which means that when I see a 6 and a 9 here, I can simplify both of those by dividing them both by 3, which means that that's going to be 3 and that's going to be 2. I can simplify the 5 and the 10 by dividing both of them by 5, and I get that is going to be 1, and that is going to be 2. Which means that really I can look at it in terms of 3 times 1 and 2 times 2 is just 3 over 4. When I turn it into a rational expression, the same logic still works. If I'm looking at these ones and I go straight across the top and straight across the bottom, then I can cancel out a y from here and here. I can cancel out a z from here and here. And I can simplify this by dividing both of them by 4 to get 3 over 1. Which means that when I do this whole process, I'm going to wind up with 3 times 3 is 9. I still have an x and an x squared. I still have one z on the top. And I've canceled out everything on the bottom, so it's all just 1, which means that I can state that it's going to be 9x squared z, and then I just need to look at all the different variables in the denominator to state the restrictions. Y can't equal 0, and z also can't equal 0. Otherwise, I'm going to be dividing by 0, and it's impossible. When I look at example B, I'm going to use the same logic. Go straight across here. And typically what I do with these variables is I would combine the variables using the laws of exponents, just to make it easier when I'm dividing. So I have a squared, the b squared in the b is going to be b3, and c4. And on the bottom, I have b squared, c and c are going to combine. I have an a cubed and I have a d, so a cubed, b squared, c squared, and d. I'm going to look at my coefficients, and I can divide the 5 and the 40 both by 5 to get 1 and 8. I can divide the 14 and the 35, both by 7, to get a 2 and a 5, which means that 1 times 5 is going to be 5, and 2 times 8 is going to be 16. And then I'm going to look at my variables. I'm going to take away 2 a's from here and 2 a's from here to be left with a singular a there. I'm going to take away 2 b's from here and here to be left with a single b up here. I'm going to take away 2 c's from here and here to be left with 2 c's up here, and there is no common d's, which means that I'm going to have 5bc squared over 16ad. And because every variable exists in the denominator, this is true so long as a is not 0, b is not 0, c is not 0, and d is not 0. I can do the same thing when I'm dealing with binomials. If I'm dealing with binomials, I'm going to go straight across the multiplication, which means that I can look at all the factors that exist when it's fully factored down. The first one is already factored down for us, so it makes our lives considerably simpler. So I can say that based on this one, I can take away an x plus 1 and x plus 1. I can take away an x plus 3 and an x plus 3. And then all I'm left with is a 2 in the numerator. And in the denominator, I have an x and an x minus 2. And I still need to state, based on all the different factors that were in the denominator in the beginning, what my restrictions are. So this is true so long as x does not equal 2, -3, 0, or -1. For example B, I'm going to factor down, and I'm probably going to expand this out just so I don't wind up making a silly mistake because that is squared. So when I say expand out, really what I mean is I'm going to rewrite it as x plus 4 times x plus 4. Visually, it just makes it a little bit easier when I'm simplifying. The top one here, I can pull out the common factor of 4, and I get x plus 4. The denominator here, I can pull out the common factor of 7, and I get 2x minus 1. And this one can't be factored down, so I'm just going to put it in brackets and say that that's going to be a 2x minus 1. And because it's a multiplication, I'm going straight across the bottom, straight across the top. I can cancel on either side. This is all going to leave me with 4 over 7 x plus 4. And looking at my factored denominators for my restrictions, this is true so long as x cannot equal -4 or 1/2. When I get to example 4, same process. So I'm going to fully factor the numerators, fully factor the denominators. That's my step 1. When I factor down the numerator, I pull out the common factor of 2m squared, and I'm left with a m minus 2. The denominator, I'm going to pull out 3m, and I'm left with m minus 3. I'm going to multiply that by factored numerator on the right-hand side, m minus 3, and m plus 2. And the difference of squares on the bottom becomes m plus 2, m minus 2. And then I can start canceling. So I take away an m from the top and the bottom, and I'm left with just one m. I take away m minus 2 from the top and the bottom, m minus 3 from the top and the bottom, and m plus 2 from the top and the bottom. And this simplifies down all the way to 2m over 3. And this is true looking at the fully factored version of my denominators, so long as m is not equal to 0 for the one outside the brackets, 3, or positive or negative 2. All right. Well, let's do the same process for this one. So I can see that there's a funny one that exists over here where I have a minus 4a cubed is going to become a and 1 minus 4a squared, which I know is in the wrong order. So I'm going to take the negative out to change the order. And then I'm going to take the difference of squares to fully factor that one down. We also have 2 that cannot be factored down by inspection, so I'm actually going to need to use decomposition to factor those ones down. So it's going to take a little bit longer. I can't just do the 2 numbers that multiply to 15 but add up to 8. So I have to actually do the longer process. So I'm going to say that this is going to be the same as when I factor down the numerator, I get a plus 3 and a plus 5. When I factor down the denominator, then I'm going to pull out a common factor of 3, which would leave me with 2a squared plus 7a plus 3. And when I use decomposition on this, I'm going to get 2a plus 1 and a plus 3 when it is fully factored down. We've already taken care of this one, negative a 2a plus 1, 2a minus 1. And on the bottom, when I use decomposition, I get 2a minus 1 and a plus 5. And now we can start to cancel out. A plus 3, a plus 3, a plus 5, a plus 5, 2a plus 1, 2a plus 1, 2a minus 1, 2a minus 1. And all I'm left with is negative a over 3, remembering that at the end, it doesn't really matter where that negative goes. And this is true so long as a does not equal negative 5, negative 3, or positive or negative 1 over 2. All right, go ahead, get some practice done.